Chapter 4 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Alex Jacoby. Science and Hypothesis by Henri PoincarÄ, Chapter 4. Let us begin with a little paradox. Beings whose minds were made as ours, and with senses like ours, but without any preliminary education, might receive from a suitably chosen external world impressions which would lead them to construct a geometry other than that of Euclid, and to localize the phenomena of this external world in a non-Euclidean space, or even in a space of 4 dimensions. As for us, whose education has been made by our actual world, if we were suddenly transported into this new world, we should have no difficulty in referring phenomena to our Euclidean space. Perhaps somebody may appear on the scene some day who will devote his life to it, and be able to represent to himself the 4th dimension. Geometrical space and representative space. It is often said that the images we form of external objects are localized in space, and even that they can only be formed on this condition. It is also said that this space, which thus serves as a kind of framework ready prepared for our sensations and representations, is identical with the space of the geometers, having all the properties of that space. To all clear-headed men who think in this way, the preceding statement might well appear extraordinary, but it is as well to see if they are not the victims of some illusion which closer analysis may be able to dissipate. In the first place, what are the properties of space, properly so called? I mean of that space which is the object of geometry, and which I shall call geometrical space. The following are some of the more essential. First, it is continuous. Second, it is infinite. Third, it is of 3 dimensions. Fourth, it is homogeneous, that is to say, all its points are identical one with another. Fifth, it is isotropic. Compare this now with the framework of our representations and sensations, which I may call representative space. Visual space. First of all, let us consider a purely visual impression, due to an image formed on the back of the retina. A cursory analysis shows us this image as continuous, but as possessing only 2 dimensions, which already distinguishes purely visual from what may be called geometrical space. On the other hand, the image is enclosed within a limited framework, and there is a no less important difference. This pure visual space is not homogeneous. All the points on the retina, apart from the images which may be formed, do not play the same role. The yellow spot can in no way be regarded as identical with a point on the edge of the retina. Not only does the same object produce on it much brighter impressions, but in the whole of the limited framework the point which occupies the center will not appear identical with a point near one of the edges. Closer analysis no doubt would show us that this continuity of visual space in its 2 dimensions are but an illusion. It would make visual space even more different than before from geometrical space, but we may treat this remark as incidental. However, sight enables us to appreciate distance, and therefore to perceive a 3rd dimension. But everyone knows that this perception of the 3rd dimension reduces to a sense of the effort of accommodation which must be made, and to a sense of the convergence of the 2 eyes that must take place in order to perceive an object distinctly. These are muscular sensations quite different from the visual sensations which have given us the concept of the first 2 dimensions. The 3rd dimension will therefore not appear to us as playing the same role as the 2 others. What may be called complete visual space is not therefore an isotropic space. It has, it is true, exactly 3 dimensions, which means that elements of our visual sensations, those at least which concur in forming the concept of extension, will be completely defined if we know 3 of them, or, in mathematical language, they will be functions of 3 independent variables. But let us look at the matter a little closer. The 3rd dimension is revealed to us in 2 different ways by the effort of accommodation and by the convergence of the eyes. No doubt these 2 indications are always in harmony. There is between them a constant relation, or in mathematical language, the 2 variables which measure these 2 muscular sensations do not appear to us as independent. Or again, to avoid an appeal to mathematical ideas which are already rather too refined, we may go back to the language of the preceding chapter and enunciate the same fact as follows. If two sensations of convergence, A and B, are indistinguishable, the two sensations of accommodation, A' and B', which accompany them respectively, will also be indistinguishable. But that is, so to speak, an experimental fact. Nothing prevents us, a priori, from assuming the contrary. And if the contrary takes place, if these two muscular sensations both vary independently, we must take into account one more independent variable, and complete visual space will appear to us as a physical continuum of 4 dimensions. And so in this there is also a fact of external experiments. Nothing prevents us from assuming that a being with a mind like ours, with the same sense organs as ourselves, may be placed in a world in which light would only reach him after being passed through refracting media of complicated form. The two indications which enable us to appreciate distances would cease to be connected by a constant relation. A being educating his senses in such a world would no doubt attribute 4 dimensions to complete visual space. Tactile and motor space. Tactile space is more complicated still than visual space, and differs even more widely from geometrical space. It is useless to repeat, for the sense of touch, my remarks on the sense of sight. But outside the data of sight and touch, there are other sensations which contribute as much and more than they do to the genesis of the concept of space. They are those which everybody knows, which accompany all our movements, and which we usually call muscular sensations. The corresponding framework constitutes what may be called motor space. Each muscle gives rise to a special sensation which may be increased or diminished, so that the aggregate of our muscular sensations will depend upon as many variables as we have muscles. From this point of view, motor space would have as many dimensions as we have muscles. I know that it is said that if the muscular sensations contribute to form a concept of space, it is because we have the sense of the direction of each movement, and that this is an integral part of the sensation. If this were so, and if a muscular sense could not be aroused unless it were accompanied by this geometrical sense of direction, geometrical space would certainly be a form imposed upon our sensitiveness. But I do not see this at all when I analyze my sensations. What I do see is that the sensations which correspond to movements in the same direction are connected in my mind by a simple association of ideas. It is to this association that what we call the sense of direction is reduced. We cannot therefore discover this sense in a single sensation. This association is extremely complex, for the contraction of the same muscle may correspond, according to the position of the limbs, to very different movements of direction. Moreover, it is evidently acquired. It is, like all associations of ideas, the result of a habit. This habit itself is the result of a very large number of experiments, and no doubt, if the education of our senses had taken place in a different medium, where we would have been subjected to different impressions, then contrary habits would have been acquired, and our muscular sensations would have been associated according to other laws. Characteristics of representative space. Thus, representative space in its triple form, visual, tactile, and motor, differs essentially from geometrical space. It is neither homogeneous nor isotropic. We cannot even say that it is of 3 dimensions. It is often said that we project into geometrical space the objects of our external perception, that we localize them. Now, has that any meaning? And if so, what is that meaning? Does it mean that we represent to ourselves external objects in geometrical space? Our representations are only the reproduction of our sensations. They cannot therefore be arranged in the same framework, that is to say, in representative space. It is also just as impossible for us to represent to ourselves external objects in geometrical space, as it is impossible for a painter to paint on a flat surface objects with their 3 dimensions. Representative space is only an image of geometrical space, an image deformed by a kind of perspective, and we can only represent to ourselves objects by making them obey the laws of this perspective. Thus we do not represent to ourselves external bodies in geometrical space, but we reason about these bodies as if they were situated in geometrical space. When it is said, on the other hand, that we localize such an object in such a point of space, what does it mean? It simply means that we represent to ourselves the movements that must take place to reach that object. And it does not mean that to represent to ourselves these movements, they must be projected into space, and that the concept of space must therefore pre-exist. When I say that we represent to ourselves these movements, I only mean that we represent to ourselves the muscular sensations which accompany them, and which have no geometrical character, and which therefore in no way imply the pre-existence of the concept of space. Changes of state and changes of position. But it may be said, if the concept of geometrical space is not imposed upon our minds, and if, on the other hand, none of our sensations can furnish us with that concept, how then did it ever come into existence? This is what we have now to examine, and it will take some time, but I can sum up in a few words the attempt at explanation which I am going to develop. None of our sensations, if isolated, could have brought us to the concept of space. We are brought to it solely by studying the laws by which those sensations succeed one another. We see at first that our impressions are subject to change, but among the changes that we ascertain, we are very soon led to make a distinction. Sometimes we say that the objects, the causes of these impressions, have changed their state. Sometimes that they have changed their position, that they have only been displaced. Whether an object changes its state or only its position, this is always translated for us in the same manner, by a modification in an aggregate of impressions. How then have we been enabled to distinguish them? If there were only a change of position, we could restore the primitive aggregate of impressions by making movements which would confront us with a movable object in the same relative situation. We thus correct the modification which was produced, and we re-establish the initial state by an inverse modification. If, for example, it were a question of the sight, and if an object be displaced before our eyes, we can follow it with the eye, and retain its image on the same point of the retina by appropriate movements of the eyeball. These movements we are conscious of because they are voluntary, and because they are accompanied by muscular sensations. But that does not mean that we can represent them to ourselves in geometrical space. So what characterizes change of position, what distinguishes it from change of state, is that it can always be corrected by this means. It may therefore happen that we pass from the aggregate of impressions A to the aggregate B in two different ways. First, involuntarily, and without experiencing muscular sensations, which happens when it is the object that is displaced. Secondly, voluntarily, and with muscular sensation, which happens when the object is motionless, but when we displace ourselves in such a way that the object has relative motion with respect to us. If this be so, the translation of the aggregate A to the aggregate B is only a change of position. It follows that sight and touch could not have given us the idea of space without the help of the muscular sense. Not only could this concept not be derived from a single sensation, or even from a series of sensations, but a motionless being could never have acquired it, because, not being able to correct by his movements the effects of the change of position of external objects, he would have had no reason to distinguish them from changes of state. Nor would he have been able to acquire it if his movements had not been voluntary, or if they were unaccompanied by any sensations whatever. Conditions of compensation. How is such a compensation possible in such a way that two changes, otherwise mutually independent, may be reciprocally corrected? A mind already familiar with geometry would reason as follows. If there is to be compensation, the different parts of the external object on the one hand, and the different organs of our senses on the other, must be in the same relative position after the double change. And for that to be the case, the different parts of the external body on the one hand, and the different organs of our senses on the other, must have the same relative position to each other after the double change. And so with the different parts of our body with respect to each other. In other words, the external object in the first change must be displaced as an invariable solid would be displaced, and it must also be so with the whole of our body in the second change, which is to correct the first. Under these conditions, compensation may be produced. But we who as yet know nothing of geometry, whose ideas of space are not yet formed, We cannot reason in this way. We cannot predict a priori if compensation is possible. But experiment shows us that it sometimes does take place, and when we start from this experimental fact in order to distinguish changes of state from changes of position. Solid bodies and geometry. Among surrounding objects, there are some which frequently experience displacements that may be thus corrected by a correlative movement of our own body, namely, solid bodies. The other objects, whose form is variable, only in exceptional circumstances undergo similar displacement, change of position without change of form. When the displacement of a body takes place with deformation, we can no longer, by appropriate movements, place the organs of our body in the same relative situation with respect to this body. We can no longer, therefore, reconstruct the primitive aggregate of impressions. It is only later, and after a series of new experiments, that we learn how to decompose a body of variable form into smaller elements such that each is displaced approximately according to the same law as solid bodies. We thus distinguish deformations from other changes of state. In these deformations, each element undergoes a simple change of position, which may be corrected, but the modification of the aggregate is more profound, and can no longer be corrected by a correlative movement. Such a concept is very complex even at this stage, and has been relatively slow in its appearance. It would not have been conceived at all had not the observation of solid bodies shown us beforehand how to distinguish changes of position. If, then, there were no solid bodies in nature, there would be no geometry. Another remark deserves a moment's attention. Suppose a solid body to occupy successively the positions alpha and beta. In the first position it will give us an aggregate of impressions A, and in the second position the aggregate of impressions B. Now let there be a second solid body of qualities entirely different from the first, of different color, for instance. Assume it to pass from the position alpha, where it gives us the aggregate of impressions A prime, to the position beta, where it gives us the aggregate of impressions B prime. In general, the aggregate A will have nothing in common with the aggregate A prime, nor will the aggregate B have anything in common with the aggregate B prime. The transition from the aggregate A to the aggregate B, and that of the aggregate A prime to the aggregate B prime, are therefore two changes which themselves have in general nothing in common. Yet we consider both these changes as displacements, and further, we consider them the same displacement. How can this be? It is simply because they may be both corrected by the same correlative movement of our body. Correlative movement, therefore, constitutes the sole connection between two phenomena which otherwise we should never have dreamed of connecting. On the other hand, our body, thanks to the number of its articulations and muscles, may have a multitude of different movements, but all are not capable of correcting a modification of external objects. Those alone are capable of it, in which our whole body, or at least all those in which the organs of our senses enter into play, are displaced en bloc, i.e. without any variation of their relative positions, as in the case of a solid body. To sum up, 1. In the first place, we distinguish two categories of phenomena. The first involuntary, unaccompanied by muscular sensations, and attributed to external objects. They are external changes. The second, of opposite character and attributed to the movements of our own body, are internal changes. 2. We notice that certain changes of each in these categories may be corrected by a correlative change of the other category. 3. We distinguish among external changes those that have a correlative in the other category, which we call displacements, and in the same way we distinguish among the internal changes those which have a correlative in the first category. Thus, by means of this reciprocity is defined a particular class of phenomena called displacements. The laws of these phenomena are the object of geometry. Law of homogeneity. The first of these laws is the law of homogeneity. Suppose that by an external change we pass from the aggregate of impressions A to the aggregate B, and that then this change alpha is corrected by a correlative voluntary movement beta, so that we are brought back to the aggregate A. Suppose now that another external change alpha prime brings us again from the aggregate A to the aggregate B. Experiment then shows us that this change alpha prime, like the change alpha, may be corrected by a voluntary correlative movement beta prime, and that this movement beta prime corresponds to the same muscular sensations as the movement beta, which corrected alpha. This fact is usually enunciated as follows. Space is homogeneous and isotropic. We may also say that a movement which is once produced may be repeated a second and a third time, and so on, without any variation of its properties. In the first chapter, in which we discussed the nature of mathematical reasoning, we saw the importance that should be attached to the possibility of repeating the same operation indefinitely. The virtue of mathematical reasoning is due to this repetition. By means of the law of homogeneity, geometrical facts are apprehended. To be complete, to the law of homogeneity must be added a multitude of other laws, into the details of which I do not propose to enter, but which mathematicians sum up by saying that these displacements form a group. The non-Euclidean world. If geometrical space were a framework imposed on each of our representations considered individually, it would be impossible to represent to ourselves an image without this framework, and we should be quite unable to change our geometry. But this is not the case. Geometry is only the summary of the laws by which these images succeed each other. There is nothing, therefore, to prevent us from imagining a series of representations, similar in every way to our own ordinary representations, but succeeding one another according to laws which differ from those to which we are accustomed. We may thus conceive that beings whose education has taken place in a medium in which those laws would be so different might have a very different geometry from ours. Suppose, for example, a world enclosed in a large sphere and subject to the following laws. The temperature is not uniform, it is greatest at the center and gradually decreases as we move towards the circumference of the sphere, where it is absolute zero. The law of this temperature is as follows. If cap r be the radius of the sphere, and little r the distance of the point considered from the center, the absolute temperature will be proportional to cap r squared minus little r squared. Further, I shall suppose that in this world all bodies have the same coefficient of dilation, so that the linear dilation of any body is proportional to its absolute temperature. Finally, I shall assume that a body transported from one point to another of different temperature is instantaneously in thermal equilibrium with its new environment. There is nothing in these hypotheses either contradictory or unimaginable. A moving object will become smaller and smaller as it approaches the circumference of the sphere. Let us observe, in the first place, that although from the point of view of our ordinary geometry this world is finite, to its inhabitants it will appear infinite. As they approach the surface of the sphere they become colder, and at the same time smaller and smaller. The steps they take are therefore also smaller and smaller, so that they can never reach the boundary of the sphere. If to us geometry is only the study of the laws according to which invariable solids move, to these imaginary beings it will be the study of the laws of motion of solids deformed by the differences of temperature alluded to. No doubt, in our world, natural solids also experience variations of form and volume due to differences of temperature. But in laying the foundations of geometry, we neglect these variations, for besides being but small, they are irregular, and consequently appear to us to be accidental. In our hypothetical world, this will no longer be the case. The variations will obey very simple and regular laws. On the other hand, the different solid parts of which the bodies of these inhabitants are composed will undergo the same variations of form and volume. Let me make another hypothesis. Suppose that light passes through media of different refractive indices, such that the index of refraction is inversely proportional to cap r squared minus little r squared. Under these conditions, it is clear that the rays of light will no longer be rectilinear but circular. To justify what has been said, we have to prove that certain changes in the position of external objects may be corrected by correlative movements of the beings which inhabit this imaginary world, and in such a way as to restore the primitive aggregate of the impressions experienced by these sentient beings. Suppose, for example, that an object is displaced and deformed, not like an invariable solid, but like a solid subjected to unequal dilations in exact conformity with the law of temperature assumed above. To use an abbreviation, we shall call such a movement a non-Euclidean displacement. If a sentient being be in the neighborhood of such a displacement of the object, his impressions will be modified, but by moving in a suitable manner, he may reconstruct them. For this purpose, all that is required is that the aggregate of the sentient being and the object, considered as forming a single body, shall experience one of those special displacements which I have just called non-Euclidean. This is possible if we suppose that the limbs of these beings dilate according to the same laws as the other bodies of the world they inhabit. Although from the point of view of our ordinary geometry there is a deformation of the bodies in this displacement, and although their different parts are no longer in the same relative position, nevertheless we shall see that the impressions of the sentient being remain the same as before. In fact, though the mutual distances of the different parts have varied, yet the parts which at first were in contact are still in contact. It follows that tactile impressions will be unchanged. On the other hand, from the hypothesis as to refraction and the curvature of the rays of light, visual impressions will also be unchanged. These imaginary beings will therefore be led to classify the phenomena they observe, and to distinguish among them the changes of position, which may be corrected by a voluntary correlative movement, just as we do. If they construct a geometry, it will not be like ours, which is the study of the movements of our invariable solids. It will be the study of the changes of position which they will have thus distinguished, and will be, quote, non-Euclidean displacements. And this will be non-Euclidean geometry. So we see that beings like ourselves, educated in such a world, will not have the same geometry as ours. The world of four dimensions. Just as we have pictured to ourselves a non-Euclidean world, so we may picture a world of four dimensions. The sense of light, even with one eye, together with the muscular sensations relative to the movements of the eyeball, will suffice to enable us to conceive of space of three dimensions. The images of external objects are painted on the retina, which is a plane of two dimensions. These are perspectives. But as eye and objects are movable, we see in succession different perspectives of the same body taken from different points of view. We find at the same time that the transition from one perspective to another is often accompanied by muscular sensations. If the transition from the perspective A to the perspective B, and that of the perspective A' to the perspective B' are accompanied by the same muscular sensations, we connect them as we do other operations of the same nature. Then, when we study the laws according to which these operations are combined, we see that they form a group, which has the same structure as that of the movements of invariable solids. Now, we have seen that it is from the properties of this group that we derive the idea of geometrical space and that of three dimensions. We thus understand how these perspectives gave rise to the conception of three dimensions, although each perspective is of only two dimensions, because they succeed each other according to certain laws. Well, in the same way that we draw the perspective of a three-dimensional figure on a plane, so we can draw that of a four-dimensional figure on a canvas of 3 or 2 dimensions. To a geometer this is but child's play. We can even draw several perspectives of the same figure from several different points of view. We can easily represent to ourselves these perspectives, since they are of only 3 dimensions. Imagine that the different perspectives of one and the same object to occur in succession, and that the transition from one to the other is accompanied by muscular sensations. It is understood that we shall consider 2 of these transitions as 2 operations of the same nature when they are associated with the same muscular sensations. There is nothing, then, to prevent us from imagining that these operations are combined according to any law we choose. For instance, by forming a group with the same structure as that of the movements of an invariable 4-dimensional solid. In this there is nothing that we cannot represent to ourselves, and moreover, these sensations are those which a being would experience who has a retina of 2 dimensions, and who may be displaced in space of 4 dimensions. In this sense, we may say that we can represent to ourselves the 4th dimension. Conclusions. It is seen that experiment plays a considerable role in the genesis of geometry, but it would be a mistake to conclude from that geometry is, even in part, an experimental science. If it were experimental, it would only be approximate and provisory. And what a rough approximation it would be. Geometry would be only the study of movements of solid bodies, but in reality, it is not concerned with natural solids. Its objects is certain ideal solids, absolutely invariable, which are but a greatly simplified and very remote image of them. The concept of these ideal bodies is entirely mental. An experiment is but the opportunity which enables us to reach the idea. The object of geometry is the study of a particular group. But the general concept of group pre-exists in our minds, at least potentially. It is imposed on us not as a form of our sensitiveness, but as a form of our understanding. Only, from among all possible groups, we must choose one that will be the standard, so to speak, to which we shall refer natural phenomena. Experiment guides us in this choice, which it does not impose on us. It tells us not what is the truest, but what is the most convenient geometry. It will be noticed that my description of these fantastic worlds has required no language other than that of ordinary geometry. Then, were we transported to those worlds, there would be no need to change that language. Beings educated there would no doubt find it more convenient to create a geometry different from ours, and better adapted to their impressions. But as for us, in the presence of the same impressions, it is certain that we should not find it more convenient to make a change. End of chapter 4.